Thank you all for coming to our second colloquium of the fall 2015 series. It's now something of a tradition that whenever we get a new faculty member or anyone else that has interest in research here in the department, we ask them to give one of our colloquia early in September. And today we're going to hear from our newest colleague, Professor Mathew White, who prior to UVM was a professor in the Department of Physical Chemistry at the Johannes Kepler University in Linz, Austria. And before that, he was a student at NRL, I guess, in Colorado, and of course the PhD was officially awarded at the University of Colorado at Boulder. He is a physicist with great interest in materials for photovoltaics, and I'll let him tell you today about the other part of his research that he didn't get to talk to us about when he was here interviewing back in January, and that is the perovskite solar cells. So, thank you.
Thank you. Thank you, Mathew, for the introduction. And thank you all for coming out this afternoon. My name is Mathew White, and I will be talking about perovskite solar cells. I'm going to start with an introduction, a little bit of an introduction to solar cells in general, because there are some physical concepts you should understand before I get to the very last few slides, which rely on the motivation that we have to derive from the basic understanding of the devices. And then I'm going to talk about the perovskite materials and the recent, let's say, revolution that's happening with respect to perovskites as a material for photovoltaics. And then I'll go on to talk about our research and our contributions to the materials, and then some demonstrations that we've done, including this fancy airplane here. So some of the people I should acknowledge, this work was done at my former institute at Johannes Kepler University in Austria. And these were some of my colleagues who put a great deal of effort into this work, so I should definitely acknowledge them. The rest of these guys are still in Linz at the moment. Lucia has moved on to the University of St. Andrews, and hopefully we can continue collaboration with them on some topics that I'll discuss at the end. And several of these people, at least these two guys, will be here in the second week of December for a symposium that we're hosting through the MRS chapter. Okay, so a little background about solar cells. Solar cells are essentially diodes that should ideally obey the ideal diode equation. But that's the ideal case, they never do quite. But when you shine light on them, they generate a current in the dark. And so you can get a power out of them in this fourth quadrant of the current versus voltage graph. And we specify the quality of a solar cell by 3 or 4 numbers. Really the metric that you're looking for is power conversion efficiency, which is often this ADA. But if you take the relevant numbers of the short circuit current, how much current is generated under one sun illumination, and the VOC, where if you open the circuit, what voltage is built up under one sun illumination, multiply those two numbers by what we call the fill factor, which describes the rectification quality of the diode, you can come to the number of power conversion efficiency. So if you report these 3 numbers, uniformly, different solar cell communities can discuss the quality of their solar cells. Another number that you might see is quantum efficiency, or incident photon conversion efficiency. This describes the number of photons at a given wavelength that the solar cell can convert to electrons. And so if you integrate your quantum efficiency curve multiplied by the incident photon spectrum of the sun, you should come to that number the short circuit current, is JSC. So a little bit about photovoltaics. A solar cell, a single junction solar cell, should consist of a semiconductor, which if you shine light on it and that light has energy less than the band gap, that light is not absorbed. So that power, that portion of the solar spectrum is just lost. And the light with energy at or greater than the band gap is absorbed, but the energy higher than the band gap is lost to thermalization, and you harvest the carriers essentially at the band gap. times the number of photons that are absorbed. And so the next few slides I'll go through what's probably the most famous solar cell paper, or the most influential solar cell paper ever written, is this detailed balance paper published by Shockley and Quasar in 1960. And essentially it says if you take the total energy out, which is the band gap times the integral from the band gap to infinite energy of the solar spectrum, and divide that by the energy that the sun puts on incident on the solar cell, which is the integral of the energy times the number of photons, you can get a theoretical maximum efficiency assuming perfect harvesting at the band gap. And that gives you this nice curve as a function of band gap of your semiconductor, with a peak of about 44% at a band gap of 1.1 electron volts. However, there's more. Every solar cell, in fact everything, radiates light. What absorbs light radiates light. And so your solar cell, as it absorbs light, it heats up a little bit and emits light. And so you're bound by this Planck distribution of electromagnetic radiation to go into thermal equilibrium between the sun and the solar cell. And what you get is that the sun and the solar cell get into thermal equilibrium. The sun occupies a tiny angular fraction of the entire sky, but the solar cell can emit in all directions. So you wind up with this consequence that the short circuit current, which is related to the absorption coefficient of the semiconductor, times the incident photon flux of the sun, is related to the dark current, the same way the dark current is related to the thermal emission of the solar cell. The same absorption coefficient times the black body radiation of the solar cell at a given temperature. That depends on what temperature the cell operates at. But here, this loss, this J0 over JSC loss, accounts for a loss in the open circuit voltage of the solar cell. So you can never have a VOC, your VOC of your solar cell will never be the band gap. It's always less because of this. And that shifts your theoretical maximum from the Shockley-Quasar limit to this curve, which has a maximum at about 33%, at a band gap of closer to 1.3, 1.4 electron volts. Okay? And this was the result of Shockley-Quasar, and trying to get solar cells to this limit has been the goal of solar cell research ever since. But there's more. That paper assumes that every carrier recombination event results in the emission of a photon, right? But there are non-radiative recombination processes. And so you can plot this same curve assuming that only a certain fraction of the radiation or the recombination results in radiation. So this green line here is 1%, 0.01%, 0.0001%, etc. down here. You see that it relatively quickly drops off. And this comes from an additional loss in the VOC related to the quantum efficiency of what we would call an LED. If you take your solar cell and drive it in forward bias, you inject current into it. Ideally, every electron that you inject will recombine with the hole and emit a photon. But that doesn't happen. You have recombination losses through non-radiative processes, and that can be quite significant. In fact, your radiative recombination efficiency for a lot of these processes is something like 10 to the minus 7. So almost no radiative recombination happens. And these are, coincidentally, the lower efficiency solar cells. Right? So we're looking for materials that have high radiative recombination efficiency and therefore very small loss in VOC. Coincidentally, all of these materials down here, amorphous silicon, dye-sensitized solar cells, organic photovoltaics, those are new technologies that people have been very excited about looking into for the past 10, 20 years. Okay? So now we're going to shift and we're going to talk about perovskites as a material. So what is a perovskite? What do I mean? Well, a perovskite is any material that follows this crystal structure that's called this ABX3 pattern. Okay? And typically, the X is anionic and the A and B are cations. They can be any number of things. They're not specific. And so the material was named after a mineralogist, Lev Perovsky, who was Russian, when another mineralogist discovered calcium titanate. So this CaTiO3 was the first perovskite discovered, but any of these combinations, and any combination including a whole lot of other things, can follow this perovskite structure. But what you'll notice is that you have this BX tetrahedron, or octahedron, that forms, and the octahedra form this kind of rigid structure, leaving a void in between where the B cation sits. You can vary that B cation and it sits in the void. This structure is rather flexible, so it can bend and distort to accommodate very large things that you stick in there. So you can stick in large functional cationic species, including big organic species. And that's what we're going to talk about, is hybrid inorganic, which forms the octahedral structure, and organic, which forms the B cation, the functional B cation species. And so hybrid materials involve a mix of organic and inorganic components, and oftentimes you can get a sum, like a sum effect that is bigger than the sum of the two parts. For example, in steel, if you mix carbon into iron, you get something that is very different from carbon or iron. You get steel. And so when you mix organic and inorganic components, you can have various types of interactions between the components, whether it's van der Waals, ionic, or covalent. And in this case, what we're going to be talking about is mostly ionic crystals. Okay? Here's just an example of when you have a hybrid species, you can have, depending on the configuration of the two, very different structural, physical, and optical properties coming out. So you can have the prismatic layer and the nacre layer in seashells, essentially. So hybrid organic inorganic perovskite materials can also be used as functional materials. They're not just structural. So the first demonstration of this that I found was in 1994. It was a demonstration of this perovskite as an LED. And so this is an organometal halide hybrid perovskite. It is phenethyl ammonium tetraiodide plumbate, or phenethyl ammonium lead iodide. And so it's called PAPI, PAPI. Okay? And so now, currently, we're seeing a perovskite revolution going on. It started a couple of years ago. Why didn't the revolution start in 1994 when these guys demonstrated that it can be used as a functional electronic material? And the answer is that it is incredibly hard to make thin films out of this salt that likes to crystallize. Okay? If you put this stuff down, it likes to form crystals with holes in it. And if you're trying to make a thin film device with two electrical contacts, and there's cracks, you're always going to have parallel pinhole shorts. So you can never measure the functionality of the device because you just can't make a film out of it. Okay? This was tried extensively, I should state, because the interest in the material has been around for a long time. And credit should be given to this fellow David Mitzi from IBM Watson Labs. He spent probably 25 years studying perovskites as a structural material and a functional material. They tried it for solar cells, they tried it for everything. And in 2007, IBM officially abandoned the project. They said, okay, no more, we've spent enough time, enough money looking into this, but we're done. And they're about 5 years too early, because in 2012, this fellow, Henry Snaith from Oxford, as well as Michael Gretzel from EPFL in Busan, demonstrated that these perovskite materials, if you can get the films done right, can be very, very good for solar cells. And so this was the first demonstration. You can see that they used a sintered titanium nanoparticle mesoporous structure. And the reason they did this was because they were coming from a dye-sensitized solar cell background. So these two groups were people that investigated dye-sensitized solar cells, which have a mesoporous titanium structure. The reason for having the mesoporous structure, they claimed in this original paper, was that it increased the surface area for this functionalizing dye, which is the perovskite. That is completely not true. Okay? It's become very clear, even the year after, Henry Snaith himself published a paper that said, forget it, I was wrong, we don't need that. But that was the original idea. It turns out that the mesoporous structure just makes making the top film easier. Okay? So this problem of making a continuous film is alleviated by having the mesoporous structure. If you could alleviate it some other way, your device or your manufacturing process would be a lot better. Okay, so just a few key points. Here we see that they had efficiency of 11%. This was in 2012, so not very long ago. But the really interesting part is that the VOC on this solar cell is between 1 and 1.2 volts. It's extremely high. Okay? And to clarify what the material is, this is the material that is of interest, of incredible interest to everybody around the world right now. This is basically what Henry Snaith used, and the only one that works particularly well. This is MAPI, methyl ammonium lead trihalide, or triiodide. And there's a lot of discussion. To make a very good film, you blend in a mixture of lead chloride and lead iodide. But nobody's been able to detect the presence of chloride in a complete film. So where this chlorine goes, nobody really knows. But there's been a lot of discussion. This is published by Maria Lloyd, a possible crystal structure, but nobody really is sure that these chlorides are still there. Okay? But you have a tetrahedron of lead, iodide, with in between methyl ammonium organic molecules. And these are little dipoles, which are loosely bound to the structure, but if you apply a field, they can rotate. And if you change the temperature, the structure of this changes, and the motion of the dipoles changes too. And so a lot of the discussion, a lot of the research going on about what's interesting about this is figuring out, well, is it the fact that the lead, this heavy atom, is here that makes the solar cells work so well? Or is it the fact that we have these dipoles here that makes it work so well? And if we make the dipoles stronger or physically bigger, does it change the performance? We don't know. Okay, so this is a famous chart that shows the solar cell efficiency for various technologies as a function of year. This is maintained by Enron and put out about twice a year. And so here you can see this is organic solar cells. These are quantum dot solar cells, dye-sensitized solar cells, and amorphous silicon. And these yellow dots inside the red circles, those are the perovskite solar cells. So starting in 2013, they started certifying them, and already they're up over 20%. Okay? And so this already high starting point and rapid rise in the efficiency is incredible. It's unmatched pretty much anywhere on this chart. And it's brand new. We're still here, so we still have work to do.
What is that right at the top?
This one?
Yeah.
These are all concentrator solar cells. So what a concentrator solar cell does is if you put a big lens over the solar cell itself thinks that the sun is close. So you lose that small angle, big angle effect from the black body radiation thermal equilibrium. So if the sun looks like it's closer, you can get a much higher VOC. Okay? And so a lot of these are concentrator solar cells. All the purple ones are multi-junction cells. Some of these are single junction gallium arsenide. Some of them are under concentrators too. So you get more efficiency by having multiple junctions stacked, and you get more efficiency by having a concentrator, and that's what these 46% ones are. Pretty much the highest efficiency single junction cells are right around here at 25, 26. Okay, so not only are the solar cells good, but everybody's talking about them. So I did, a couple days ago, I did a brief search on amorphous silicon solar cells, on ISI, on P3HE polymer solar cells, which are two very hot research topics over the past decades, and on perovskite solar cells. And you can see that until 2012, nobody was writing about perovskite solar cells and nobody was talking about them. But after 2012, it just spikes. And already this year, which is not even finished, there are more publications on perovskite solar cells than there were on polymer and amorphous silicon solar cells put together. So this is a really hot topic in the solar cell research community. Everybody's looking into it and everybody's talking about it. And so, you know, if the efficiency is already at 20%, what are we still trying to do? Well, there's a few things. One thing that's very exciting is that right now, we have this MAPI material has a band gap of 1.55 eV. The efficiency is right here around 20%. But if we look at the loss in energy, the loss in voltage, silicon has about 400 MeV, gallium arsenide has about 300, and perovskites have between 350 and 450. Okay? So that means that they should be, in terms of radiative quantum or efficiency, they should be very good, which means that the theoretical limit should be somewhere up here, right next to gallium arsenide or crystalline silicon. Okay? So just based on the material itself, we think that we can get that efficiency up higher. So what is exciting? Well, they already have an extremely high efficiency of about 21%. They have a theoretical efficiency of about 26%. There are so many variables to turn from a scientific standpoint in terms of what the materials are, A, B, and X. They can be processed from solution. They can be processed from vacuum at low temperatures. Both of those things are good for making high throughput production. And it's brand new. And it's already among the best of the best solar cell technologies. Okay? So what's wrong? What are the problems that still need to be solved? Well, one of them is film formation. Okay? Like I said, you can process these guys from a vacuum source. You can pump down a chamber, heat up two sources, one with the methyl ammonium, one with the lead iodide, and co-deposit them onto a substrate. And you can make pretty nice films of this, but once you reach a certain critical thickness, they start to crack and form non-continuous films. Okay? And with solution processing, it's even worse. There are ways you can fine-tune it to get a nice film, but once you get too thick, they start to crack. So eventually we're going to need some kind of crystallization revolution, something like the Shklorovsky method for forming crystals of this lead iodide to make real thick solar cells. Because we can, at the moment, absorb a good fraction of the light, but to absorb all of it, you need it to be a lot thicker than we can make the films.
So why does a film crack in general?
Because it doesn't necessarily crack. It's just that as you grow, certain peaks start to form, and then they are growth sites for the next layer. So as you're putting down the next layer, it will preferentially stick to the tallest thing.
So non-uniform growth.
Yeah, you get non-uniform growth, essentially. And you have mobility if you're coming from solution. Everything's mobile, and it will just stick together into these tiny salt crystals, and then those will grow. So rather than making a continuous film, you get something that looks like this. Okay? Yeah?
And you need thick films rather than multiple film layers? Like you can't just stack?
You can stack, but if you're going to stack solar cells, it's better to stack solar cells with different band gaps. And so that's one way to do it. If you can do sequential processing cheaply to get a tandem cell, you could have a high efficiency cell, but usually it comes with a high cost as well. Okay. Another critical issue is the stability of these cells. If you make this solar cell, the perovskite solar cell, and you encapsulate it extremely well, then it's fine. It lasts pretty well. But if any water vapor gets in, the water vapor attacks the perovskite and releases hydrogen iodide gas, which kind of bubbles out. And that, in turn, attacks the electrode, which makes the electrodes fall off, which exposes more of the surface to the water vapor, which is a self-catalyzing reaction, and these things die very quickly if there's any exposure to ambient air. So that's a real problem. Okay? And the last one is toxicity, right? We're using lead iodide, and this is a water-soluble lead salt. So if you do have a good encapsulated solar cell, that's fine, but if you put it on your roof and a hailstone hits it and it cracks and then it rains, you're getting lead running down your roof into your garden maybe or wherever, and I don't think anybody wants that. So there's a lot of discussion. You can replace the lead relatively easily with tin in these structures, and so people say, oh, well, if we just replace it with tin, we'll be fine. But I'm not so sure that's the case. I don't want tin running down through my water either. I mean, there's a reason. I'm not a chemist per se, but there's a reason that still a coupling is banned is because organic tin compounds are pretty toxic. Okay? So let's move on now and talk about some progress that we made over the last year in Linz. So for those of you who were at my talk last January, you may remember that I discussed this idea of our ultra-thin devices, our thin film organic solar cells. We use a foil that's 1.4 microns thick. It's 10 times thinner than kitchen wrap. We build solar cells on top of it, and then we can use them as very lightweight power sources for certain applications. But there were a couple of problems. One is polymer solar cells are not very efficient, so perovskites looks like a pretty good avenue to take. But also, if we're going to make any real progress with this, we need them to be air stable, because the devices that we made before had calcium in them, and calcium is extremely unstable in air. And we need large area films, because if you want to really use solar cells for anything, having a tiny, tiny one won't even power your calculator, so who cares? So we need to solve, if we want to use perovskites for ultra-thin solar cell applications, we need to make some significant progress in terms of the air stability, and we need to find a way to create large area films reliably, so we'll explore the crystallization mechanism. So the materials that we use in our devices, we use this methylammonium lead triiodide perovskite. We do process it from lead chloride, but as I said, there's no evidence that the chlorine stays in. We use this conducting polymer, P.PSS, as a selective hole contact and a transparent electrode. And we use these two materials as selective electron contacts, and then we use polyurethane as an encapsulating layer. It's not a very good encapsulant, but it just prevents the devices from being scratched. When we make our devices, we make them all in ambient air. So that's also an important thing to note, because a lot of people spend an inordinate amount of effort trying to protect the materials from air, but it's really okay to process them in air to a degree. So the structure, the ideal structure that we want is we want our 1.4 micron thick foil, our transparent electrode, perovskite, our electron selective contact, and a back metal. Polyurethane encapsulant is optional. It doesn't provide much other than structural support. If we look at these first two layers, from the polymer work, we can easily do plastic foil with PDOT on top. It's a question of getting the perovskite to form on top of that. Okay? And a lot of people who come from an organic PV background have tried this and failed, or struggled, at least, let's say. So if you do that, this is an optical microscope image here. You shine light up underneath, you can see, just with your eye, that there are holes. There are a lot of holes. And there are a lot of holes in every, let's say, 10 micron square centimeter, or square. If you want to make a device that's square centimeters or even square meters large, and you have 100 holes in every square micron, you're not going to get it to work. Okay, so this is completely unacceptable. And so what we came up with was, when we put this PDOT down on the plastic foil, if we just spin the perovskite on, you get these crystals that grow with massive holes in between, very regular massive holes. The devices won't work at all. And what we found is that if we infuse the PDOT layer with a very high boiling point solvent, DMSO, and DMSO is a good solvent for lead iodide, that this layer retains the high boiling point solvent for days. It might never come out, we don't know for sure. But then when you put the perovskite on top of it, it maintains an amorphous layer right at the interface. And that causes the crystal growth to be much more compact, so that the gaps in between fill. And what we see is that by adding DMSO, a little bit at a time, to the PDOT, we can wind up with very uniform perovskite films. Okay? The DMSO has an added bonus that it increases the conductivity of the PDOT itself by a factor of 2. So if we're trying to use it as a transparent electrode, now we can get working devices over very large areas reproducibly and high conductivity electrodes. So what do we do about electron selectivity? Well, because we come from an organic solar cell background, we said, oh, this is the best electron selective material we know. We tried it. It works, but this itself is very air unstable. So we pretty much ditched it right after we showed that it works. And we selected this material, which is a very old organic semiconductor, a very old N-type organic semiconductor. And it's called PTCDI. This is a red pigment that's found in a lot of cosmetic products, in paints, and it's very stable. So you can leave this stuff in air in the lab for decades and it doesn't bleach, it's fine. It's very good rock solid stuff. And it works as well or better than PCBM did, so for us it was a no-brainer to just use this PTCDI as an electron selective capping contact on top of the perovskite. But what do we do about the metal electrode? Okay, because as we said, if any water touches this perovskite layer, the perovskite layer forms, iodide comes out of the perovskite and comes up and bubbles up to the surface, which causes the electrode to delaminate. Which seems like an insurmountable problem. What we've been using, what everyone's been using up to this point, is gold. And most of us device people think, oh, gold, it's stable under everything. But the one thing that you can use to etch gold in the semiconductor industry is iodine. Okay? So here we have this lead iodide crystal where iodine is leaching out of it due to the water vapor and producing the one thing that etches the gold. Okay? So this is a real catastrophic problem. This causes the gold, where the bubbles come out, to delaminate, and then it causes more water to come in, and it catalyzes the death of these solar cells. And so what we did was we deposited a very thin layer of chromium under a slight oxygen partial pressure to get a chromium oxide sticking layer right at the surface. Chromium oxide is very stable against these halogens. Okay? You put down this chromium oxide layer, and I demonstrate this here. I put this slide in for my students who showed up, thank you. Because this is the XPS, X-ray photoemission spectroscopy data that shows that we do have this oxidation state of the chromium at the interface. And this is an extension of the photoelectric effect that we did yesterday. Okay? So we can really use it. So we put this chromium oxide layer in, and then the devices become much, much, much more stable. Okay? And I'll quantify that later. But more importantly, it allows us to use gold or cheaper metals like copper or aluminum. It doesn't matter. We can put whatever metal we want on that back. Right? And the devices are equally stable and equally efficient. Okay? So here's a picture. Here's what the devices look like, the end devices. This is one with gold back electrodes, and this is one with copper back electrodes. And these are on the ultra-thin foils that are peeled off of their supporting substrates. So you can kind of see them bending. So taking a closer look, we can see an SEM image of the surface of the perovskite. We see that we do have microcrystals, but they are pretty compact. There are no real holes in between them. Okay? And if we do a cross-sectional TEM, we can see the thicknesses of the respective layers. So they're all there. Okay. So how do the devices work? Well, they work reasonably well. Okay? We can get 12% efficiency out of the devices with about 18 milliamps per centimeter squared and a very good fill factor, but a VOC of only 0.9 volts. Okay? And there's virtually no difference between those made on glass as to those made on foil, which is good. But more importantly, we can make a lot of them and they all work. Okay? And that's a direct result of Adam's hard work in finding a recipe for this p-dot perovskite layer to make uniform films repeatedly. Okay? Otherwise, there's no way this is possible. So we made roughly 170 solar cells, and we can say that, look, there's a real distribution of efficiencies, of open circuit voltages, fill factors, and short circuit currents that peak around, let's say, 18 milliamps per centimeter squared, 12% efficiency, fill factor of over 70%, and VOC of around 920.
What is the fill factor?
Fill factor is the metric that describes the rectification of the diode. 100% fill factor would mean if you had a diode that went straight over and then straight up to infinity, which is impossible. So the highest you could hope for is, say, like high 80s, but that's very, very rare. Okay, so the next question is device stability. We said we improved our devices by incorporating the chromium oxide, but what does that mean? Well, we measured the devices not only sweeping the current voltage curves, but also by implementing a maximum power point tracking software on the solar simulator. There's a reason for that. We show here out to 1,000 seconds, which isn't so long, but you can see that it's stable at around 12% efficiency. The reason we had to do this is because within the perovskite community, there's a big discussion about whether you should sweep forward or sweep backwards, because perovskites exhibit a hysteresis because those dipoles can flip. Okay? And so this is a big source of debate, but for solar cells, you don't want to be sweeping when you're using them. You want to just put them on a load and let them generate power. So this is the best way to really characterize power. But then we just let that run over the course of a day or two, And under continuous operation with absolutely no encapsulation, so we make the devices, we just take them out in the lab and put them under the solar simulator, they can operate for a day of continuous operation before decaying to 80% of their power generating capacity, which is remarkable. If you take this device, which is the same device without chromium oxide, expose it to air for 10 seconds, it already loses, let's say, 70% of its power generating capacity, and then it dies within an hour completely. That device will last for 2 years if encapsulated. This one, if encapsulated, presumably will last for a lot longer. We don't do long-term device studies, so this is the extent of our data on that. But because we can use them unencapsulated outside for days, that means we can do real-world devices, which is kind of what we wanted to do to begin with. Okay? So we made these ultra-thin solar cells, and they are 12% efficient. So if we put them under one sun illumination, we get 120 watts per meter squared out of the devices. But they only weigh 4.6 grams per meter squared, which means that they give out 26 watts per gram of solar cell. And this metric, specific weight, the watts per gram of the solar cell, is useful for things like space applications or for military applications. If there's a soldier who has to carry these things in his backpack for about 3 months, he wants them to generate a lot of power without much weight. Or if you are going to do research in the Arctic or something, you have a lot of space, but not much weight to carry. And these ultra-thin perovskites are by far the highest of any photovoltaic technology ever. And I think they're the highest of any power generating technology ever because you don't need to bring the fuel with you. Okay? So, but I can't really back up that claim. I've looked at a few other technologies and none of them come close. Okay, so here's a demonstration. We just stuck it on a leaf skeleton just kind of for PR purposes. But that's working outside, no encapsulation whatsoever. Okay, the next thing we wanted to do is to make little aeronautic demonstrations that we could power flight with solar cells. And now in the lab scale, we couldn't make enough solar cells to fully cover these wings, but we could easily make enough to cover this tail section and connect them directly to the motor. Okay? And by doing so, we get 8 substrates, each with 8 solar cells, so roughly 64 solar cells. And we connect them, and we get a module, a mini module, that puts out 75 milliwatts. Okay? And this would not be possible if any one of these devices didn't work. Okay? This is 100% pixel success rate. So here's just a video. This is a little bit superfluous, but so we put together this model airplane, and you can see the solar cells here. These aeronautic demonstrations were done in February in Linz, Austria, which is about 5 or 6 degrees further north than we are now. And so there's not much sunlight really, but nonetheless we can get these airplanes to fly. They don't take off on their own. But we can get the airplanes to fly around using only the power of the sun. Okay? Let's see.
Why is it falling down? It's not hitting the sun.
What's that?
Why it's falling down?
Well, the plane will always go down eventually. So depending on the wind and the sun, it will fly around.
It's away from the sun, that's why?
No. It just kind of goes at random. And it's very light, so if there's any wind, it blows where the wind wants it to go.
So the gravity is more than the...
If there's enough sunlight, it will keep going on its own for a long time. But this is really slow. There's a great scene at the end where it crashes, so I'm just okay. So that's the solar powered plane. Okay. We also made, we made a solar powered blimp. This was something that the head of our institute has been insisting that we do for about 3 years, and we finally got a chance to do it. This works also. There's a video, I'll just show you a brief clip of it. But the solar panels turn the propeller and the blimp flies around, but similarly, if there's any wind, the blimp goes away. Okay, so with these thin film devices, we can also enable stretchable electronics. So they're thin enough that if you take an elastomer like a rubber band, stretch it, you can glue the film to the top and relax it, and it will form a network of wrinkles and folds to conform to the elastomer without damaging the devices themselves. Okay? And these wrinkles and folds sometimes have radius of curvature down to 5 or 10 microns. Okay? Very small wrinkles, very small folds, but almost no damage to the devices. We do that by, we have this little jig where we can stretch the elastomer, put the device on, wire it up, and then relax it and contract it, or expand it and contract it repeatedly. And when you do it, the solar cells still work just fine. Okay, this is not too surprising to us by now. It's a little bit surprising that this inorganic crystal, the perovskites, can withstand it, but we know that because the film is thin, there's not much stress in the actual semiconductor itself, so this is not too surprising. It's kind of a nice demonstration that the technology is robust under this kind of deformation now. These are the various stages of compression here, down to about 50%, and then restretching to flat, and the device works exactly the same. Here you can see the normalized solar cell metrics as a function of compression. And so you see that as you compress here, I'm sorry, this is not power, this is power density. As you compress here, you get less current out of the solar cell. And that's because there's less incident area. So there's less light incident on the solar cell. But if the current were to track exactly with the compression ratio, you would expect the current to decrease along this flat line here. So what you're seeing is actually an increase in the performance of the device because you are collecting more of the photons that are emitted. Because if go to the next slide, if you look here at this microstructure, when a ray is incident, there's multiple chances for the ray to reflect off of several of these valleys before it gets reflected back into space. So if the light is not absorbed, here it has more chance to be absorbed. And you see that in the quantum efficiency here, where at higher compression, you have a higher overall quantum efficiency. Okay? So it's essentially like taking a flat solar cell and making a pyramid structure on the front just by compressing it. These solar cells are, I mean, you can stretch them, but how many times? Well, we stretched it, we have an automatic stretcher, we stretched it up to 100 times, and after a while they do start to die, but that's probably just due to micro cracks forming in the metal electrode. We're not exactly sure what the primary mechanism is, but I would suspect it's cracking of the metal. And for one last demonstration, we did what we call radial stretching. So rather than just stretching in one dimension, we took this elastomer and stretched it like a spider web, stuck the solar cell on and let it relax. And you can see that it forms this really ugly network of wrinkles and folds. And likewise, you can compress it and stretch it and it still survives. Okay, and here's just a video of what that stretching looks like. This one's also a little slow.
What's the scale of that?
So each of these is 2 millimeters wide, or 3 millimeters wide by 5 millimeters long from about here. This, from here to the end, should be 5 millimeters when it's flat. Okay. So we think that by enabling this film forming layer on the P.PSS, we were able to make large area electrodes, or large area solar cells, or relatively large area solar cells, repeatedly on very flexible substrates and use them for the demonstrations that we wanted to. But there's a sacrifice, and that is the VOC. In our devices, in all of our devices, the VOC was under 1 volt. It was some 920 millivolts. But the reason perovskites are really exciting is that you can get 1.1 volts out of the VOC. So we're losing something there. So we wanted to figure out why. And so we looked at the photoluminescence of these films when they're on different layers. And what we noticed is that here's the absorption of the perovskite layer. You see it cuts off right at 800, corresponding to the band gap of 1.55 dB. And if you look at the photoluminescence, you have a nice sharp peak right there at 800. But if you put the perovskite layer on top of P.PSS, boom, the photoluminescence is completely quenched right away. And this ties back into what we said earlier about the radiative versus non-radiative recombination. Perovskite by itself has a lot of radiative recombination, but when you put it on P-dot, it's gone. And so that pretty much accounts for exactly our loss in VOC. What we did was we operated all of the solar cells as LEDs and measured the quantum efficiency of the LED, so the electroluminescence quantum efficiency. And we plugged that in to this equation that was specified by Rao here. And our prediction based off of this analysis comes out to be exactly what we measured. If you assume that there's only radiative recombination, you have left unaccounted for this 300 or 400 millivolt loss. But it can all be accounted for by this loss in the luminescence, which is present in both photoluminescence and electroluminescence. So this is a real problem if we're going to use this electrode. So either we have to replace the electrode with something that doesn't quench the luminescence, or we have to find out why that is. So in conclusion, I hope that I've convinced you that perovskite photovoltaics is a booming material revolution, at least in the research field. And a lot of technological industries are very interested in it. We at Linz provided some key contributions to film uniformity on a large scale. And by large, obviously, kilos. I don't mean large, I mean large. And to the device stability. Because having devices that you can put under a solar simulator for an hour unencapsulated and have them stay stable is pretty incredible. We demonstrated PV-powered flight. We demonstrated durability under extreme deformation and the highest power per weight of any photovoltaic technology. The fundamental questions still remain. What is the interfacial mechanism that causes its luminescence quenching? And that's exactly what my postdoc Lucia went to St. Andrews. She went to work with Ivor Samuel. And hopefully we can stay in touch and maybe we can write a joint project to analyze it, because exactly the kind of ultra-fast spectroscopy that Madalena does and that Ivor do are what is needed to answer that question. And really, what mechanisms can we preserve from the perovskite material? Which are the key mechanisms that cause the solar cells to work well? What can we preserve when we replace the lead and the iodine? Because the iodine is going to be sensitive to water no matter what, and the lead is going to be toxic no matter what. We want to get rid of both of them if we can, but we might not be able to. So with that, I would like to acknowledge all the rest of my collaborators in Linz, our funding agencies, the ERC and the FWF, and thank you for your attention.
So the floor is open for questions.
Yeah, Adrian.
This Mathew, or this material that works so well, so what was the, I mean, why was that selected? Is it just random chance that they mix those things together, or was there some DFT predictions that that would be a good material to begin with?
No, so I don't know the exact origin of it, but it was a pretty well-known hybrid material. And there were demonstrations of these organic, inorganic, like this 1994, the PAPI LED. So they have good optical properties. And the idea, the original idea from the dye-sensitized groups was that they would try to coat just 1 or 2 nanometers surface of the TiO2 structure with this perovskite, and then have a hole-conducting solid-state electrolyte surrounding that. They didn't realize that it would be such a good semiconductor by itself. So it was selected for a completely different reason than why it works so well, is the short answer.
You mentioned all of the structural changes that can take place, the tilting of the octahedra and rotations of these dipoles. I assume that these are very soft modes.
Yeah.
Not a lot of bearing to the rotation of the dipole. Is Is that
I think
correct?
so,
Yeah.
yeah.
So I would expect that there's strong electron-phonon interactions in these materials. Is that known to be true, just included?
I'm not sure. I'm not sure what literature's out there on that. Yeah.
So your large size, which is about millimeter size, right? And then open circuit, the output voltage is more or less like less than 1 volt.
Yes.
And what is the output impedance this device have?
The output impedance of a solar cell, you want to put a load impedance that matches the power output impedance. And that scales with area. So if you make the area larger, you have to make the load resistance smaller. And so for these, we can use 10 or 100 ohm resistors to operate them at maximum power point. But if you make the cells bigger than, say, 3 or 4 square centimeters, then you need to start connecting them in series so that you don't get the high currents. So you can add voltage to maintain a low or a reasonable matching impedance.
So to increase the power, then you have to put the device in parallel? Or
No, in series.
In series.
Yeah. So the devices we had, I'm sorry, they were put in parallel. We just connected them all in parallel. But there were 8, that was 64 small devices, so it was still reasonable. But if you need to go larger, then you have to connect them in series.
Yeah, and if you in parallel, then the output voltage is more or less like 1 volt.
Yeah.
And then quite a lot of applications requires more than 1 volt.
Yeah.
And then so how are you going to overcome this problem?
Well, you just connect them in series.
Just put them in series as well?
Yep. Because then you take, if you connect them in series, you keep the same current but add the voltages. If you connect them in parallel, you keep the same voltage but add the currents.
I have a question related to excitons and the morphology of the film. You showed an image earlier, I think it was either TEM or SEM. I don't remember. The one where you showed the grains, right? The grain sizes. And yeah, this one, exactly. So my question was, is it only in plane disorder, or do you also have crystallites that are rotated, basically? The crystalline axis rotated.
I imagine you have some.
Out of plane.
Yeah, I imagine you have some of both.
So it's not inconceivable that you would have plane boundaries even, throughout the thickness.
Well, the thickness, hold on.
Vertical
So
or horizontal grain boundaries.
it could, but look at the thickness here. It's 200, 300 nanometers.
Yeah.
Compared to the grain size, which is several microns. So it's not inconceivable, but primarily I think you're looking at single grains.
Yeah, I guess I'm trying to connect that to the non-radiative pathways
Yeah.
in the film.
Well, the same film, if you just take away this P dot, they're perfectly radiative, right? So the material itself
So
is
you're
good.
happy with
just-
you're happy with the efficiency of radiative recombination in the absence of P dot,
Yes,
the way the film
it's just
structure.
fine. Yeah, and it's the quenching at this interface which causes the loss of the. Yes.
Is there some kind of a junction? Is there a PN junction?
So what we have is just a semiconductor with 2 selective contacts. And so you have a gradient buildup because electrons can easily leave one way and holes can easily leave the other way. And so you get a concentration gradient that drives the current.
So is it like Shotkeys?
It's essentially like 2 Schottky junctions, one on either side, yeah, an N selective and a P selective on either side. Yes.
On the hobbyist side of things, for your solar-powered airplane, you said highest energy density per mass. Is there a limit? Like, if you had covered the wings, with the solar cell, would it have flown better, or?
Oh yeah, for sure.
So why just the?
So one of the things, like, when we had this plane, somebody asked why it was going down. The reason it was going down is because if you want the plane to fly, it has to fly like this, but in February in Linz, the sun is over there. So if we pointed the plane like this, the propeller spun like crazy, but then it would go straight down or straight up, and you didn't have that much power. But if you did the same thing, if you said, well, we just covered the whole area, we get more power, the propeller spins like crazy for sure. So yeah, and so
And
over
it's not
time,
heavier than that thin membrane you were using for the wings anyway, or such.
The
like you're
thin
adding-
membrane for the wings was the same membrane that we used for the solar cell.
Right.
So they're not much heavier.
Right.
They just have a tiny layer of grown gold on top of it.
So this problem of having the lead in the middle, so one is you are trying to replace that with tin.
That's one option, yes. And people have done it. It's been done. It was done within a year after the first lead iodide perovskite papers. The efficiency is less than half. And so far, nobody's been able to get it up that high. And one possible explanation is that these carriers live a long time. The heavy metal centers are useful in inter-system crossing. So you generate singlets and they transform to triplets, and so those live a lot longer. So you get longer lived carriers in the presence of the lead that you don't get in the presence of the tin. And so if that's the case, if you have to have the lead to get that, then what are you going to do? And that's an example of what I mean by how can we preserve the desirable mechanisms without keeping the lead.
So what other material other than tin?
Well, you can, I mean, certainly you don't need to stick with the metal halide. You could explore the entire perovskite material space.
Okay.
But so far, finding materials that work well is not easy. Unless you know the mechanism that you need, you're kind of just shooting fish in the barrel or shooting randomly.
So you think there's not a lot known in terms of the excitons and what happens to them in this system?
Well, I think there is a lot known, but not a lot agreed upon. So a lot of those papers that are published discuss this phenomenon, but you can read 5 different opinions in 5 weeks. So there's not a real uniform consensus.
Can you say something about the cost of these? Is it all very cheap to make at this point?
Yeah, I mean the projected cost, if you look at materials cost, it's cheaper than a lot of things, unless you consider the cleanup of lead from the environment. So you say, well, if we assume that they never spill and we can harvest them all and just recycle them at one recycle center, the cost of making them is very low. You can make them from an ink, so you can print them like newspapers. So the processing cost is low, the material cost, there's nothing very expensive here. Presumably it's about as low as you can get for solar cells. The real cost of like a silicon solar cell comes from the high temperature processing, and then you have to slice the devices up and process them one at a time. Here it's just all inline processing.
If we get over the lead poisoning problem and say that you coat it with something that's more durable, could you see this being implemented like in replacing silicon solar cells or in addition to a different context?
I think that ultimately, if the cost is low enough, you'll see it replacing. The only thing that anybody's really interested in terms of solar industry is making a lot of power from solar. Like the small applications are worth doing from an industrial perspective. So, yeah, if the industries are going to become interested in it, it's absolutely to, let's say, replace silicon. You can also think about making a silicon perovskite tandem cell, but you don't gain much in terms of advantage. So, yeah, so it would be as an alternative probably. Yes.
Are there different perovskites for different band gaps?
Yes. I mean, the tin analog, so if you just replace lead with tin, and you have methyl ammonium tin iodide, it has a different band gap, has a lower band gap.
So you can make layers structured without much more cost?
Presumably. The problem with making layers is the same with any sequential layer processing. It assumes that your bottom layer is perfectly flat and indestructible by the techniques that you use to deposit the second layer, right? And if I have a lower layer that's soluble and I put a solvent on top, it's going to dissolve the first layer, unless it's protected somehow. So that processing, that process engineering has to be really specific to say, well, I'm going to put down something, then I'm going to protect it before I put down the second layer, and the protecting layers can't interfere with the device. Okay, does that make sense? So it's not easy. It can be done, but it's not easy.
So the second layer, or the protecting layer, has to allow the minority carrier, or the carriers to travel.
Right. You are processing essentially a recombination layer that also protects the film from the processing of the second layer on top. So for example, you could put down zinc oxide or something. Zinc oxide is pretty robust to a lot of conditions, and then when you put down the second layer, the zinc oxide acts as a recombination layer, but doesn't dissolve in the DMF when you put it on top. Something like that could work.
But the carriers have to go in both directions.
Right.
Through that layer.
Well, yeah, they don't have to travel through. That has to act as a recombination center. So electrons from one cell go and holes from another cell go. They recombine. And so you cancel the current but add the voltage as you go up the stack. So one electron doesn't have to travel from the bottom cell all the way back to the electrode. It goes to the recombination layer in the middle, and then the corresponding electron that was generated in the top cell goes through the circuit at a higher potential. Yeah?
So this problem with the low voltage is because of the PDOT PSS.
Yeah.
But this layer is just to close the holes. But
it serves two purposes. It is the transparent electrode, so we have no way of contacting it without it, unless we replace it with some kind of metal, which we could do, but metals tend to be less transparent.
It seems like you're getting an unwanted electrical property from a material that is doing something structural.
Well, it's doing something structural and electrical, but you could replace it with graphene or carbon nanotubes, or theoretically you could put down anything else that is conductive and transparent. You can even sputter ITO, but that's not flexible. But that's okay. I mean, if you want to make an ITO device that's not so flexible, there's a lot of reason to do that. Yeah.
If you look at the graph D, where the light coming in?
This is a TEM, so it's actually the electrons that are coming in. So we have cross section, we put it at an angle and just do a TEM image. Okay.
Right, but the top is gold. Right.
Yeah.
But that's the electron.
This is the electrode, yeah. And then on the bottom we have the plastic foil. So if this was the solar cell, not just in the microscope image, but if this was a solar cell, light would come in from the bottom here. Yeah, through the plastic, and then this PDOT PSS that I was talking about with Adrian, it's transparent and conductive. So this is an electrode, and this is an electrode here.